Hi everyone, my name is Dongqi Han from Okinawa Institute of Science and Technology. Today I'm going to introduce our work, Self-Organization of Action Hierarchy and Compositionality by Reinforcement Learning with Recurrent Neural Networks. The central concept of this work is hierarchical action. And for us, the humans, when we learn to make a cup of tea, our brain can autonomously divide the task into multiple abstracted actions, such as adding hot water and putting tea bag in and taking tea bag away. And those abstracted actions can be further divided into more detailed actions, such as finger movement and foot movement. So we might ask a question, how the abstracted action can be learned by brain. So this work is to computationally understand the mechanism of how the hierarchy of action can self-organize by exploration in sensory motor learning. And by self-organize, we mean there's no teacher providing task hierarchy to the agent. The agent need to recognize the hierarchy of action autonomously. Since we are talking about the brain, is there anything notable in it? First, it is found that there is a ascent hierarchy of timescales in the cortex. The brain regions that are believed to handle higher level cognition has longer timescale. Also, cortical neurons have highly stochastic firing behaviors. Finally, cortical circuits are recurrent. So these three factors are what we are considering in this work. Hierarchy of timescale in the neural network, and also stochastic neuron behaviors. And we will use a recurrent neural network to model those behaviors. We use reinforcement learning as our computational scheme. So in reinforcement learning, there is an agent interacting with an environment by executing action A, and the agent will observe a state S and reward R from the environment. The objective of reinforcement learning is basically to get more rewards. And one thing is how to choose a good action. We use a policy function, also called actor, to model the probability of choosing action A given current state st, pi A given st. Also, it is important to estimate how good is a current state. So we use a value function, also called a critic, which estimate the cumulated discounted future rewards using policy pi. So V pi st is the expectation under policy pi of the current reward plus gamma times the reward from the next time step plus the reward from the next time step times gamma square. So here gamma is called discount factor, which is a value between 0 and 1, and it controls how far the agent will consider future rewards. So when gamma is large, the value function will consider more about future rewards. Oppositely, when gamma is small, especially when gamma equals to 0, it is the case that the value function only model the current reward. Now let me introduce the proposed model, REMASTER, the abbreviation of Recurrent Multi-Level Actor Critic with Stochastic Experience Replay. We use a recurrent neural network with two levels as the main structure, where the higher level has a slower timescale of neuron dynamics, and the lower level has a faster timescale of neuron dynamics. Correspondingly, the higher level recurrent network estimates a longer term value function, namely with a larger discount factor, and the lower level estimates a shorter term value function. Besides that, the policy is stochastic, which is necessary for exploration. The neurons in the network have a stochastic dynamics similar to the real cortical neurons. And we use standard reinforcement learning algorithm, TD learning, temporal difference learning for the value functions. Except that there are two value functions with different discount factor gamma, which is different from normal case. And the policy gradient algorithm is used for learning the policy function. Importantly, unlike many other hierarchical reinforcement learning methods, we do not design algorithms for learning the action hierarchy. But action hierarchy is expected to autonomously develop during reinforcement learning just to get more rewards. There are two key elements in this work. One is the intrinsic hierarchy of timescales in the network, and the other is noise in the neural dynamics. We will try to answer the two questions by running simulations. First question is, are these two elements enough for self-organizing action hierarchy? And the second is, are these two essential for self-organizing action hierarchy? Here is more details about the network, which is also known as multiple timescales recurrent neural network. The hidden states of the else level is indicated by UL, where L equals to 1 is the lower level and L equals to 2 is the higher level. The parameter tau L indicates the timescale of the L level neural dynamics, which is 2 for the low level and 8 for the high level in this work. And tau decides how fast hidden states U can change. When tau is smaller, the hidden state U will change faster. And the two levels are connected as shown in the diagram or in the equations. Here, W is the weight and B is the bias. The RNN output C is the hyperbolic tangent function of hidden state U plus a noise term. And the noise term is a unit Gaussian noise epsilon times noise scale sigma, which is fixed in our simulation. Then the value function of the two levels can be estimated using RNN output C1 and C2 respectively, and the policy function can be given using the low-level RNN output C1. Again, the two important elements are multiple timescales and the neuronal noise. So the task we considered is so-called multiple target reaching task. There is a two-wheeled robot on a plane. It needs to reach 3 targets in the sequence of red, green, and blue so as to get reward. And the difficulty of this task is that there's no external signal to indicate which target to go. So the agent must recognize which target to go using its memory of historic observation. For example, after reaching red, you need to think, oh, now I have reached red, I need to go to blue. So this can be achieved by using a recurrent neural network. And the sensory input for this robot is basically the distances and angles from 3 targets. And we can see that it's clear there's a 2 level of action hierarchy. The lower level is to control 2 wheels for target reaching using sensors, and the higher level is to recognize which target to go now. And here is a video of a trained agent. So you can see, it can successfully fulfill this task by first go to red and then green and blue. So our remaster agent, after enough training, can reach more than 95% success rate. So knowing that the remaster agent can successfully learn this sequential target reaching task, let's do some analysis of the neural activities, because we are interested in how the action hierarchy can be self-organized in the network. So first we can see here we plotted the behaviors of the same agent in 3 different episodes. So each column plots 1 episode, and we can see that in the bottom, this is the actual trajectory on the 2-dimensional plane. So the black square indicates the initial position of the robot, and the colored circles are the target positions. So you can see that the configuration of the 3 episodes are different, but the agent can always successfully finish the task. And the interesting thing is, if you look at the high-level RNN output of these 3 episodes, we can zoom in to see it more clearly. And so here in the plots, the horizontal axis is a time step, and the vertical axis is the high-level RNN outputs of different neurons indicated by different colors. And the vertical dashed lines indicates the robot reaching first target or second target or third target. So you can see that although the configuration of 3 targets are quite different in these 3 episodes, but the temporal profile of high-level RNN outputs are quite similar. If you look at the sky blue curve, this neuron always activity always goes up after reaching the first red target, and goes down after the second green target. And in other for other neurons, it's also similar. So somehow we can see that the high level represents a subgoal, and by contrast, if we look at the low-level RNN output and also the detailed action, which is the speed of 2 whales, we can see that they are less similar among episodes, because they need to deal with the detailed motor control to reach certain targets. To see this more clearly, we plot the principal components of RNN outputs for both the high level and the low level. We plotted data from multiple episodes. The data points from the same episode is linked by black lines. So here, this PCA plot shows how high level and low level neuron activities represent the subgoal. So when the color is darker, it means the robot is more closer to the corresponding target. So you can see that the in the high level, there is a more consistent representation for the subgoals. However, in the lower level, it is relatively less consistent because the lower level also need to deal with detailed motor control. And we can also do a PCA for the 2-level RNN outputs, but this time the color indicates the detailed motor action, which is the left wheel speed and right wheel speed. So you can see that here we plot the first 3 principal components. You can see that in a lower level, there's a relatively more clear representation for the low level action, while in the high level, the representation is not as clear as the low level. This is because the high level doesn't need to deal with very detailed wheel control. So based on this, we can see that an action hierarchy emerged, and so the high level RNN learned subgoal representation from reinforcement learning, and the lower level is more corresponding to detailed motor control. So remember that remaster agents do not have an explicit objective to learn the action hierarchy, but the action hierarchy comes from self-organization by reinforcement learning. Since our previous analysis indicates that the low-level learned control skills for achieving each subgoal, relearning to solve a new task, that is a recomposition of previously learned subgoals in a different sequence should be much more efficient than starting from scratch. By considering this, we carried out another experiment in an extended version of the sequential target reaching task, referred to as the consecutive relearning task. In this task, the robot agent needs to adapt consecutively to change the task goals by relearning. The consecutive relearning task consisted of 3 different phases. Phase 1 is the same as the original sequential target reaching task, and phase 2 and phase 3 appeared as novel recomposition of subgoals, where the required sequences are green, blue, red, and blue, green, red, respectively. While phase 1 had 12,000 episodes, there were only 3,000 episodes in phase 2 or 3. So we plot a performance curve indicated by success rate of finishing a task. And you can see that remaster is compared to 3 alternatives. One is remaster single V, in which the high level, it is the same as the remaster, except that the high level doesn't estimate a longer term value function. And also remaster deterministic, which is also same as remaster, except there's no neuronal stochasticity in neuron dynamics. Finally, it is compared with LSTM, in which we only use a single layer LSTM for this task. And LSTM has an adaptive time scale, but there's no intrinsic hierarchy of time scale, and LSTM estimates a medium-term value function. So we note that in the relearning phases, phase 2 and phase 3, remaster performs better than the alternatives, in which either timescale hierarchy or neuronal noise is missed. So these results show that these 2 key elements, timescale hierarchy and neuronal noise, they are essential for better performance. Recall that in the brain and also in remaster, there's a ascent timescale hierarchy in which the higher level has a slower timescale. So how about a different timescale hierarchy if we reverse the timescales tau in the neuron dynamics of the high level and the low level, or we reverse the discount factor for the 2-level value functions, what will happen? And we found that the original setting, where the high level has a slower timescale, has the best performance. This result can be a potential explanation of why our cortex has an ascent timescale hierarchy. This is another interesting result. You know that the remaster agents have learned to solve the sequential target reaching task, in which it needs to reach 3 targets in a sequence, and we found that the high level learns to represent subgoals. How about if we want it just to accomplish one subgoal, such as going to the blue target? Actually, this can be done easily because this is an artificial neural network. We can manipulate neural activities. For example, we can fix the high-level neural activity to the values same as those when the agent approaching blue in previous trials. So here is the video of what will happen. So you can see the robot goes to the blue target and keeps wandering around this blue target. Because we fixed the value of the high level. Also, similarly, we can fix the high-level neural activities to the values same as those when the agent approaching green. And the video shows the agent goes to the green target and it consistently pursues this subgoal. And we can also do the same thing for the red target, and you can see that as expected, the agent goes to the red target, and it just keeps approaching this red. even it doesn't get any reward. Let me shortly summarize this work. So we focused on a type of sequential compositional task, and we investigate how the tasks can be solved by autonomously developing subgoal structure. We proposed a remaster, which is characterized by two essential features. One is the multiple time scale, and the other is the neuronal stochasticity. And our simulation results showed that there's a action hierarchy self-organized by reinforcement learning. And this compositionality developed in previous learning enabled efficient relearning in new tasks, which is a recomposition of previously learned subgoals. Thank you for listening to the presentation. And this is the Cognitive Neuron Robotics Research Unit in Okinawa Institute of Science and Technology. If you are interested in the technical details of this work, welcome to check our paper with the same title. Thank you very much.